Okay, so with Taylor series expansion, then what are the effects of beta of omega? For example, we have a piece of dispersive medium with a thickness L, and the medium has beta of omega, propagation constant beta of omega. And in general, we can send an input light. The spectrum is big E sub in of omega. The time domain function is small e sub in of t. This is your input electric field as a function of time. And we have known, according to the carrier envelope representation, your electric field can be written as real part of temporal envelope function, small a sub in of t, times the carrier function e to the j omega 0 t, where small a function is a complex function, envelope and the phase. Okay? How about the output? This is the central issue of the modeling. This is your input. This is your material. What is the output? Very easy, right? Because beta means wave vector or wave number. Then what is the contribution of the material? It will contribute to a phase, which is beta times interaction distance L. That's it. Okay? So the modeling is like this. The output spectrum is equal to the input spectrum times a pure phase modulation in the frequency domain. And the phase is beta times L with a minus sign, coming from the plane wave model, e to the minus jkz, right? So that's why this is the central issue. Okay? The material's contribution is only characterized here, a pure phase modulation minus beta times L. But what about the corresponding electric field as the output? It's like this. Electric field as the output equals real part of new envelope function times new carrier function. Okay? But be careful, your output carrier is this, different from your input carrier. In addition to omega 0 t, which both have in common, you have an extra term minus beta 0 times L. Okay? And that's what I need to elucidate. The output carrier is this, or can be rearranged as this one. Okay? Extract carrier frequency omega 0 out of the parentheses. T is preserved, and the beta 0 times L equals omega 0 times tau p. And the tau p is beta 0 times L over omega 0. Okay, just a rearrangement. Then it means the output carrier experiences a phase delay of tau p. Tau p is a physical quantity about time, right? 因为挂号 t 减 tau p 代表 tau p 跟 t 是同一个物理量时间。那 input carrier e to the j omega 0 t, output carrier e to the j omega 0 parenthesis t minus tau p. What does that imply? It implies it takes a time interval of tau p for the carrier to pass through this material, right? 你比较一下这两个函数，进来是这个，出来是这个，全部都一样啊，只有一个只有一个 time domain shift。那是不是代表我的 carrier 花了 tau p 的时间通过这一块射散材料 ？Okay, that's the meaning of phase delay. So if it takes tau p to propagate over a distance L, what is the corresponding speed? Speed means the distance over the required time, right? So speed Vp equals L over tau p. By substituting tau p with this formula, you got this omega 0 over beta 0. This is the well-known phase velocity formula, right? And the discussion shows that phase velocity is the velocity of which wave? The carrier wave, right? Nothing about the envelope, pulse envelope, just carrier. This is the velocity of your carrier. Okay. How about the envelope? Okay. Because the output spectrum is related to input spectrum by this relation. So there is a transfer function relation. What is transfer function? If you studied the linear system theory, what is transfer function? If you have a linear system, in the frequency domain, output equals input times a transfer function. OK， 那也没错嘛。Output 是 input 乘上一个 transfer function. This is transfer function. OK， but if the total spectrum is related by a transfer function relation, so does the spectral envelope function, right? 也就是小 a 的 spectrum 叫大 A 嘛，小 a 的 spectrum 叫大 A， 大 A 的 input 跟大 A 的 output 之间也是一个相同的 transfer function relation. Okay, so that's it. Output spectral envelope equals input spectral envelope times a transfer function. And the transfer function, according to the deduction here, is a pure phase modulation function. And it's everything except for the contribution from beta 0. Remember, in the previous page, the tidal series expansion shows beta omega is equal to beta 0 plus higher order terms. And the contribution due to beta 0 has been already taken into account in the analysis about carrier, right? 我们是不是在这里已经把贝塔0用掉了？所以这里的零阶泰勒展开项的贡献已经被用在这里了。剩下来就是给 envelope function 的 modulation. Okay? So that's why the phase modulation for the envelope is the beta omega minus beta 0. So it contains beta 1, beta 2, beta 3, and all the higher order terms. Those terms together will modify your spectral envelope function. Okay, any question? Now, we need the help of Fourier transform property again. Very similar to the case about cell phase modulation. Here, in general, nonlinear spectral phase modulation results in a new temporal waveform. Okay? So big F and a small f are Fourier transform pair. If you multiply big F with some nonlinear phase modulation function, then you got the new spectrum, big F prime, and certainly a new temporal waveform F prime. And there is no clear relation between small f prime and the small f, because delta omega in general is a nonlinear function. There is no clear relation. But you can borrow the Fourier transform property. We know a shift in the time domain, okay, f of t minus tau is the same shape but displaced by a distance tau in the time domain. The spectrum is the original big F spectrum times a linear spectral phase modulation function, e to the minus j omega tau. Okay, that is what we have known before. And then you can compare the phase modulations. In general, it's delta psi. In particular, it's minus omega tau. So you can conclude the nonlinear phase modulation results in a frequency-dependent temporal shift, or usually the term group delay. The symbol is tau sub g. This is a group delay function. It's not a constant, it's a function of frequency, which is the derivative of your spectral phase modulation function with a minus sign. Just comparing these two phases, you can get this conclusion. Okay? And if you substitute the delta psi of omega by the previous, the formula in the previous page, you got beta 1L plus beta 2L times omega plus beta 3L over 2 times omega squared and so forth. Okay, this is the Tyler series expansion of the group delay function. Okay, is the concept okay for you? Fourier transform property. A shift in the time domain means a linear spectral phase modulation function in the frequency domain. Now, my phase modulation is in general a nonlinear function, not a linear function. But it doesn't matter. Just performing first order derivative, you should be able to get something like tau, the time delay, right? But this time, if this is a nonlinear function, derivative is not a constant. It's a function of frequency. So you have a shift tau, but it's not a constant shift. It's a frequency-dependent shift. So that's why it's termed group delay function. Okay? Maybe some view graphs. This is the original spectral function, big F of omega. The blue one is the phase, assuming initially the spectral phase is constant. And the gray one is the corresponding temporal function, temporal waveform. Then, if you apply a linear spectral phase function, minus tau omega here, so you have a linear function. This is a phase function, and with a minus sign, that means negative slope. What is the corresponding waveform in the time domain? Just first order derivative, so you got a shift by a constant amount of tau. That's it. Okay. Second example, what happens if now your phase modulation is a quadratic function, minus mu omega squared over 2. Mu is some positive number. So you have, this is a convex spectral phase function. The same power spectrum, but different phase function. What is the corresponding temporal waveform? Again, you have to apply first order derivative, right? So if you perform first order derivative, you got a linearly varying group delay function, mu times omega. Mu is a positive number. So it implies the larger the frequency, the larger the delay. Larger delay means later time, right? Smaller frequency, smaller group delay means earlier time. Okay? So what's the illustration? If you observe a low frequency at omega 1, maybe here, and the group delay implies your temporal shift is mu times omega 1, which is negative number. So if the gray one is the original temporal waveform, the frequency omega 1 sees a waveform here in an earlier time. And the higher frequency component, omega 2, is a positive number. So you see the temporal waveform at a later time. Okay? So starting with lower frequency, end up with higher frequency. Okay? So basically, you will see linearly increasing local frequency. This is also upchirp, right? 越后面你的震荡频率是从低频震到高频，对不对？震荡频率逐渐递增，这个叫做 upchirp。So if you have a quadratic spectral phase modulation like this， 凹口向下的你会得到 upchirp。Conversely, if you have a concave function， 凹口向上的 phase modulation function， you will get downchirp。OK， 你得到相反的结果，高频先出现，低频慢出现，频率是递减，这叫 downchirp。OK。
在就是拿一个探测器看
OK， 想象一下，我拿一个 filter， 只把 omega 1取出来。然后我拿一个侦测器看什么时候我量到，跟我把 filter 拿到 omega 2， 只让它取出来，同样侦测器看什么时候取到，这两个时间一早一晚。他讲的意思是这样。OK。那你如果不用 filter， 你直接去量，那当然你要想象你有一个侦测器的速度快到连 fringe density 都可以量出来，你就会量到，我侦测到的讯号是从低频开始越量越高。好，如果你不加 filter 就是这样。OK。Then start with dispersion-free media is the easiest. The meaning of dispersion-free is beta 2, beta 3, and so on are all 0. Okay. Then your group delay is not a function of frequency but a constant because group delay function tau of omega 本来有 beta 2, beta 3的贡献，因为它们都已经是0，统统拿掉了，只剩下 beta 1的贡献。And group delay is equal to beta 1 times L. So you see no variable omega at all. It's a constant. So group delay is a constant. Then it means all frequency components, no matter what is the corresponding omega, spend a common time, beta 1 times L, to pass through the medium of length L. 就是不管你这 color 是什么，通通花一样的时间叫 beta 1 L, the common group delay, 来通过这个厚度为 L 的 material. So what is the corresponding velocity? Same thing, the propagation distance L over the common time required to pass through, and substitute the common time tau 0 by beta 1 L, and L can cancel with each other. You got 1 over beta 1. Okay, this is your group velocity. The velocity of the pulse envelope, right? And the meaning of beta 1 is actually first order derivative of your propagation constant function calculated at carrier frequency. And this is already well known to you, right? The formula of group velocity is 1 over beta prime. You have known that before. Here is a derivation in a different approach. Okay, and another important point is if the material is dispersion free, all the frequency components propagate at the same group velocity. It means your pulse envelope will propagate without distortion. The shape is preserved. If it is a triangular shape, it will remain triangular all the way. If it is a Gaussian shape, it will remain Gaussian all the way. Okay? Provided your material is dispersion free. But if your material is not dispersion free, it's dispersive, what happens? For simplicity, we assume two things. First, the material is normal dispersion, so beta 2 is not 0 and positive. Okay? Second, quadratic term dominates. So it means quadratic term beta 2 times omega. Omega is replaced by delta big omega, the bandwidth. Okay? Omega is a variable, it changes. But delta big omega is a constant, it's the bandwidth. So we use the bandwidth to estimate the impact of the signal. So this is the contribution from the quadratic term. And this is the contribution from the cubic term. And if the quadratic term is much bigger than the cubic term, you can neglect the cubic and even higher order terms, only preserving the contribution from the quadratic term. Then group delay is a function like this. Beta 1L, same thing as before, but this time you have beta 2 times L times omega. This is a linear function of omega. So now, different omegas will see different group delays. So different colors will spend different times to pass through the same material. So what would happen? Your pulse envelope will distort during propagation, right? The shape cannot be preserved. Okay. So if under our assumption, beta 2 is positive, so beta 2 times L is positive. The slope is positive. Then it means the larger the omega, the larger the group delay. That means it takes longer time to pass through the material, or it is slower, right? 要花比较久的时间，就代表它跑得慢。所以高频跑得慢 ，blue color is slower. Conversely, red color is faster. So this is the nature of normal dispersion. Blue part takes a longer time across the medium, then accumulated at the pulse tail. So it is up chirp again, right? So just like this figure, initially we assume chirpless pulse with uniform fringe density in the time domain, electric field in the time domain. If you have a normal dispersive material of thickness L, this is the output. Okay? As I mentioned, blue part accumulated at the pulse tail, so slower blue. And the red part accumulated at the pulse leading edge, faster rate. Okay? So this is time axis. The later time means the tail. The earlier time means the lead. Okay? So you have a up chirp. Your local frequency or fringe density increases with time. Okay. That's the case of normal dispersion. And conversely, if your beta 2 is negative, this is negative, so you have something different. You have down chirp if your beta 2 is negative. And besides, you can also imagine, because the separation in time, blue parts separated from the red part, so the envelope will be stretched. You have a stretched width, broader pulse width. Okay? 所以有两个 impact， 一个你的 fringe density 会递增或递减，第二个你的宽度会展宽。这就是 dispersion 所造成的影响。那这个展宽就代表什么 ？Envelope shape distortion. The shape is no longer the same as the input. Okay?